The next talk is by Tatiana Statsenko and Alexander Hirner, and who are both at Moonvision, and it will be about lessons learned when running an always-on Dask cluster for computer vision. Go ahead.
Thank you for that presentation. So in this talk, we're going to discuss the lessons we learned while running modern computer vision tasks on always available Dask cluster. First, I would like to shortly say what actually Moonvision does. So the Moonvision platform is an online toolbox that provides a labeling tool with a recommendation system and data management system, and we also serve various image processing tasks. So, for example, one of the most advanced self-checkout systems in Europe runs with the help of the Moonvision platform. As you can see, it works with the food and the checkouts during the canteen hours, which means we would have a very high computational load during specific time intervals, and we want to be able to serve them whenever they're needed. Also support the more idle times for our system. And for that, we are heavily rely on Dask for its computational scalability and versatility for real-time tasks. So as for real-time, we are working with object detection. We provide a label recommendation and such tasks as sprite views when you crop images and stack them together to show in real time. However, we also want to process some batches of images or videos for tasks such video image extraction or object detection. From the Dask collections, we only use delayed and futures, which means we are basically building our own custom graphs, and we do not use any data frames or arrays. So in this talk, we will start with the description of the platform system architecture, and then we will go on with our 4 main challenges that we encountered in the last couple of years, present our current solutions. We will be very open for the discussions afterwards and your experiences with this, and we will close up with some further thoughts on improvements and other ideas. So for the architecture, I give word to my colleague, Alexander.
Thanks, Tanya. Yeah, so what did we end up with from 2017 when we first decided to use Dask to now when we scaled out both in terms of available tasks and the volume of requests and so on. Dask stayed with us, the infrastructure evolved, and this is what it evolved into. So we built our inference code and the code that actually does the image transformations with PyTorch OpenCV on the lower level. It gets combined in the CI/CD step into Docker images. Combined means here with the Django server, and yeah, this updates the Helm charts. The Helm deployment is then pushed to Google Kubernetes engine, and finally the user sees API endpoints specified in OpenAPI and or React endpoints. And what are the clients? It's users sitting in front of the screen, labeling and kicking off processing tasks. It is IoT devices that request cached intermediate results from computer vision tasks or save new data into it. And it is operators like us to run research close to research processing tasks in batch. And the main components are 2 node pools. So each node pool, so for CPU workers, we have 1 node pool, and for GPU. And in these node pools, we have fixed workers on non-ephemeral nodes. And whenever there is room for additional workers, scalable workers, they usually land up on ephemeral nodes, which are cheaper. But if they don't exist, then the auto-scaling kicks in. And this is done twice, once for GPU image heavy and once for CPU only. And both are controlled from a Django server. The main things here to remember is autoscale, automatically if ephemeral is available, so it's cheap. If not, fall back to fixed nodes to scale up, and that the code is shared between workers and the Django application, which means the workers can write to the database, they can read from the same cloud buckets as the front end. And yeah, it's a really tightly integrated system by today.
Okay.
So on to the first challenge.
Yes. So the first challenge we chose is out-of-memory errors, and the use case for it is the image detection on a batch of hundreds of images. We talk here hundreds, thousands. The maximum case was about 10,000 images that we wanted to process altogether. And since we create the custom graphs starting with loading images and then processing and saving, we notice upfront that Dask would load all images into memory since the resources are available, but since it's not aware how much memory would be needed for the next processing steps, and the decompressing of the image will create an explosion of 10 times more resources needed for it, we would just block all the further computation and would not proceed any further because it would just scream that it runs out of memory. Here we can see, okay, when we're building the graphs, we cannot even optimize them automatically because there is some knowledge that we cannot tell Dask upfront. So for this challenge, what we did, we basically said, okay, we have to fuse nodes manually up to the highest memory consuming one. So we build our smart graphs based on the knowledge of what exactly our nodes are doing. And in this particular example, we merged the loading and the detection nodes to a single one, load and detect, single name. And this way, we would already not only facilitate the depth first processing for Dask, but we also can have this constant memory load for such batch processes. And as an example, we show here the small video of the 10 images being processed in parallel, and what you can also see that the nodes are being released because they're not needed anymore, the ones in the blue. And then after the processing will be finished, then everything will be in a second magically released, and bam, the scheduler is completely empty and everything is finished. This way, we can create graphs of arbitrary widths, let's say, which means that we can always support any custom graph with any batch size and not care how many images we have processed. So neat and yes, smart graph composing when you do a custom graph creation. So we move on to the challenge 2. Right. Yes.
All right. So as introduced, we have these two challenges that fight each other: batch processing when it's needed and real-time when it's also needed. And real-time for us means low latency tasks, always available. And those are especially when we embed, so-called embed parts of images, so objects, into lower dimensions, so-called fingerprints. So we need to load images, partially crop them, put them through a PyTorch model, and then store them in the Redis system, or use them directly for classification tasks onward. So also then to support the labeling, these fingerprints, they are regenerated upon a new image. So we have new recommendations coming in, and it's shared between as many people that label at the same time in real time. And then we have very complicated inference pipelines consisting of multiple PyTorch models in sequence and in parallel, and with different post-processing nodes as well, like smoothing the contours of the segmentation, etc., etc. And for these requests, the requirement is to run within 1 second and without compromise, that they are blocked. And they come in at random times and basically in a long tail fashion. So you have a few models that are very used very often, that are deployed very often. Then you have a long tail of very new models that are not used very often, and a long tail of very old models that are also not used very often. But if they do, you shouldn't fail, and you shouldn't have to wait. So the issue is here how to serve these random requested random times fast. What we needed to do is to use distributed variables to control the cache lifetime of the future explicitly. So imagine a model is anything between 20 and 500 megabytes. That alone takes 2-3 seconds to load. It can also fail to load because of I/O errors. And we control the lifetime explicitly by getting the intermediate results of such long loading tasks, getting the future, and then putting them on a distributed queue alongside with the timestamp. The timestamps and queues and futures of the models are checked regularly in a separate Python process that runs all the time. We call it cache processor. It loops through them and removes the 2 old ones. This has the effect that the first request is slow, the following requests are fast, really, really fast. So we use and abuse Dask here as a distributed cache and computation. So the kitchen sink for us in this regard. And yeah, we obtain basically a hands-off operation of these clusters, of this cluster, because we don't need to know upfront what's going on. It will adapt accordingly to the needs. Yeah, and if you use a model again, the timestamps are refreshed, so it stays for the times we set, like say 6 hours in the memory. Yeah, and if that is in place, the request times are well below 1 second, and we show that on the next demo video. So here was a call request. Yeah. The image is analyzed, usually between 0.3 seconds, 0.5. Then the front-end latency comes in via the release queue, the notification, and it shows also in the front-end. So this is against the production cluster.
There's no speedups here.
No speedups. So very impressive in terms when you compare it to like Celery, where we have a very strong isolation. This tight integration, the deserialization mechanisms is just really helpful. We had to go through many other challenges, like the pickling of PyTorch models that was not supported when we started using it in 0.4, but meanwhile it's amazing. So next one.
Yes. Next one is task prioritization. So as we mentioned already before, we have different types of tasks. Some we call real-time, which would need immediate response for the user, and the others we would just submit and wait for the response. So if we would run them on a single worker, the long-running task would just block scheduling of the real-time tasks, or we will end up that the long-running task already filling all the threads. So scheduler just cannot start any real-time tasks. So we have to find a way how we would separate them so that we can always execute real-time tasks, but don't just stop the long-run ones. And for that, we did several things. So we took profit from the logical restriction through the worker resources. We also use prioritization, and then we also ended up with the separation of computation. So basically, we built a wrapper for Dask compute and added a bunch of keyword arguments. Here, we are only interested in 2 ones. It's the fast lane task and using the GPU if available. So for the fast lane tasks, we set up the real-time resources and set up a high priority. And if the GPU is available, then we set the resource to be GPU. And the availability of the resources is set up in the environmental variables, which means that we can use exactly the same code for our production environment, for our local environment, and we just use what's available there. So when you create a worker, you can already provide, okay, use the real time, or I don't, I have just a default or GPU, everything. And historically, we created a second scheduler with a GPU worker for the image detection, object detection tasks. So we noticed that even in real time, we are more interested in the responses from the image labeling rather than the other real-time tasks, and they start still to compete with each other. And we ended up creating a separate, completely separate scheduler that is always available, GPU, so that we can provide these blazingly fast responses, as Alexander showed in the previous slide. Yes, so for this, I think yes, I like. I don't know what else to add here for this one. The last but not least, handling error tasks. Here I would like to describe two use cases. The first one is we load a model for a computer vision task, but it fails. And as we already mentioned, we actually want to cache them, and these are pure tasks. So unless we clear it up from memory, nothing will change. It will just error all along, unless we notice it, and then we or restart or we try to cancel it. The other use case is when just a complex graph that requires a lot of memory errors, and then the user would just try to restart it. So it's not cleaned up. It will end up clogging up the whole memory, and nothing else could be started then. First, we thought, okay, we just cancel or release the end future that erred. But it turned out that the only thing that happens is the graph is removed from scheduler, and we lose all the information about any processing happening there, but the memory is not freed up. So we were thinking, okay, how we would handle then such error and especially pure tasks. And in general, the complex graphs that would just not release their nodes and then the memory. So the solution is again twofold. We want not only delete the latest errored future, but we want to delete all the tasks and their dependencies from workers, which we perform by function when we run on scheduler function in client. And we pass all the keys we want to delete from worker. And we go up to the very first one that is connected to this error task. And as for the models that we're caching, we added a done callback that happens upon the loading of the model. So we check the result of the future, and if it's errored future, then we just do not add it to our cache queue, which means that you can always rerun the failed model when it's fixed, hopefully, and then no one will need to restart the whole cluster and lose all other tasks that are happening in the meantime. So last but not least.
Right, so it's not the end. We've come, I think, a long way, and we've greatly benefited from the Dask community, and really do not look back unless there's lots of failures. But then we power through, as we just seen. We'd be very curious on a few features in the future. For example, the dual scheduler setup that we have came out of necessity, maybe not the best configuration to begin with, but right now we think we could remove the second scheduler if there was something like worker affinity. So right now the logical resources are hard constraints. So if there is no GPU available, you schedule something with the GPU resource, like one element, GPU 1, greater than 0, it would be scheduled as worker not available if there is none. There are other options where you would constrain a task to a specific set of workers, but here we are not sure if some race conditions would get at us. This would be done with allow other workers. you would need to read before the list of workers. You have determined the resources, say those are the subsets of workers having these resources that I already know statically, and then put them into the worker constraints and not the resource constraints. Yeah, so worker affinity, like in Kubernetes, is something that would help us to then remove one scheduler, very likely. The next point where we will be working on is not only auto-scaling from ephemeral nodes to persistent nodes, but to vary the number of workers with the load, adaptive scaling. And here our very complex setup with heterogeneous workers does not fit well to the Dask Kubernetes adaptive scaling plugins or things that are available, because who tells them which kind of worker to scale up in terms of, so the reverse basically. Resources are done for scheduling, but for scale up, maybe that would be a good idea to then go to a heterogeneous worker scale up. And last but not least, we're using Prefect as well. That's not running in the cluster, it's running offline in our research cluster, where we have much more complex control, like need control flow over much more complex graphs. They span the whole data sets from many projects, and they are run separately. And we use Prefect for observability and the control flow. And eventually, I think those two systems could marry into an always-on Prefect cluster. So what we here are looking at is the combination of cached futures and Prefect execution, which there is, I think, not the direct solution, and maybe some other things. But yeah, really enjoy this tool as well, and happy that they are also part of the community. Well, that said, hope it was interesting so far, and me and Tanya are looking forward to your questions.
Yes, there is something here, right?
Really nice. Do you want to?
Really nice. I cannot open it. Can you open it?
Oh yeah.
Yeah, I can read the questions so that everybody hears them. But thank you for the presentation. The first question is from Adam Fries comments, really nice work. Have you investigated using Dask to train your models as well?
Yes, there is the most elegant approach, data parallel training. I don't remember who started it. There was a very good blog post going alongside the the pip library. And I think this is the most sane approach. So to have the Dask, the indices of PyTorch telling you which task worker you are. So basically the fork of it, and having some global variables in the beginning for the resource access. This would be the way to go. I think architecturally this approach is very nice, and I would need to look it up. Maybe you also mentioned it, the DTL task. Maybe I can post it then in the Slack channel.
Yeah, that is good. If you can find it.
But it's, yeah, that is one of our next steps I didn't mention.
Okay, thank you. The second question is your cluster running at your company, or do you deploy a new physical device with the Dask cluster running at the clients?
Interesting questions. We have a singleton platform that runs in the middle of Europe, and 2 clusters, staging and production. And that's running in Google Cloud, Kubernetes Engine. And we have other Kubernetes clusters in-house, but at no point in time we directly provide a scheduler to premises of someone else. Our Internet of Things devices are run in isolation, unless they need to. So they are partition tolerant with internet connectivity and therefore platform connectivity. And here it is a much more bare bone custom application that communicates with the clusters. Hope this answers the question.
Okay, thank you very much. That's all the questions we have for the time being. So that is the end of this presentation.